for the sound and the screen. Okay. Yeah, so I'm planning to talk about homework 4, and I think this is also showing on the screen. Perfect. Yeah, let me know if the brightness, or if it's too bright, or if it's not easy to see. So maybe we can first talk about exercise 1. We're given x1 and y1 as a pair, and then from 1 to I, from 1 to n, and then we are giving by very normal distribution with those parameters. They are also independent, so that's a keyword. Maybe we'll be using that somewhere in our solution. What is the joint for x bar and y bar? Hint: find the moment generating function and then compare to the joint of the multivariate normal. Okay, so that defines the way that how we're going to work on that. So moment generating function, x bar and y bar with t1 and t2. Here we're going to use the definition for the moment generating function, t1 x bar plus t2 y bar. That's just the definition for the moment generating function. And now we're going to replace the x bar and y bar by their form as a sum from 1 to n over n. Okay, and here's the t1, and then t2, y1 to yn over n. Okay, now it just depends on how we are going to group these things. So we are group them in a following way, where we combine the x and y with the same index. That means we have e of t1 multiplied by, maybe I'll also bring the n in here. So each of them share a scalar of 1 over n. So I'll bring the 1 over n to each of the t. And then x1 plus t1 over x, y1. Okay, and now we are also going to use the independent. Okay, because they are independent, we can rewrite this as a bunch of products. Expectation, e, and then all the way to the last one, tn over n. So this n is the subscript n, and then xn plus tn, t1. Sorry. Yeah. Yeah. So this is t1. So each of them, they share the same, the two t1 and t2. But the random variable is indexed from 1 to n. So t2 over n, y, n. And this is because of the independence. Okay, so now we have each of them is essentially the moment generating function for xi and yi with t1 and t2. Any questions so far? So the t index 1 and 2 is shared across all the random variable, but the random variable is indexed from 1 to n. Yeah, so each of them, they are essentially the moment generating function for their the index for x and y, but with the same function or input to the function t1 and t2. Question? Yeah. Sorry, what?
The input be t1 over n and t2.
Perfect. Yes. Yeah. Yeah. If you write t1, then yes. Yeah. So yes, very good point. Yeah. Here you can also refer like a t star 1, and t star 1 is t1 over n. Yeah. Thanks. Yeah. If you want to be precise, yes. Yeah. t1 over n. The t1 here is referring to the original t1. But yeah. Nice. Yes. Yeah. So if you write the T1 in terms of the original T1, then this is T1 over n, and this is the T1 star. Like, yeah, perfect. Yeah. Any other question or comments? Okay. Maybe let's move this, and then yeah, this is just a bunch of moment generating function for xi, yi, yes, t1 over n and t2 over n, and then n copy of them. Well, if you want to, yeah, this depends on how rigorous you want to write it. But you can write x and y here if you want. Yeah, depends on how rigorous you want to be. Yes, so it's just n copies as a product of n moment generating function, and from here, once we transform from where we start from x and y, x bar and y bar, and back to individual random variable that we know they are bivariate normal, now we can substitute with the moment generating function of bivariate normal into the square bracket. So e raised to the power of yes, t1 over n. So the t1 here is still referring to the original t1 multiplied by the mu vector. Okay, in that case then n is a scalar, t1, then let's write it as a vector then. Okay, so 1 over n, and this t is a vector transposed by the mu of the y1 and y2. So x and y follow a normal mu, so they are in R2, and then sigma, referring to covariance. This is 2 by 2. Okay, so if you write x and y into a vector in R length 2, then here I'm referring to t as the vector, and then don't forget a scalar 1 over n plus 1/2, and then t over n as a vector, but scaling by a factor of 1 over n, sigma matrix, and then t over n. Yeah, and then you have n copy of them. Yeah, here we just plug in the moment generating function because we know that x and y followed by very normal. Yeah, and then now we just need to bring in this n here. N copy of the products of the exponential is the exponential of sum. So you have a sum over n copy of this. I mean in the power inside here. So basically just multiply by n in this in the exponent here. So you have t transpose mu, and then plus 1/2. And then depends on how you want to write it. So there's also this is a 2 by 2 matrix, and then scaled by a factor of 1 over n, and then a vector t. So we so here we fix the t as a vector, but we put the n, this factor, to the covariance. And then we are trying to match the moment generating function of a bivariate normal. Then you can recognize this having the normal distribution with mean mu, but covariance matrix that is scaled by a factor of 1 over n. So this is a 2 by 1, this is a 2 by 2, but scaled by a factor of 1 over n for each of the 2 by 2, 4 elements in that. So now we can write x bar and y bar if you want to write it as a column vector following a bivariate normal with the original mean that is inherent from the original x and y. But the covariance matrix has to be scaled by a factor of 1 over n. And then you probably want to just based on my preference, you probably write 2 as a dimension there. But yeah. Any question or comments? Or any typo that you might find? Okay, next I'm planning to talk about exercise 4. Okay, so x1, x2, a column vector, followed by very normal. Consider the vector y1 and y2, where yi is defined as exi. Okay, and then I range from 1 to n, 1 to 2. This is referring to the coordinate, not for how many elements, how many observations that you have. We are interested in y1 raised to the power of 3, and the covariance between y1 raised to the power of 3 and y2 raised to the power of 3. Okay, so we are interested in these 2 quantities. Okay, first of all, let's start from the momentary function of vector x, where vector x is referred to the column vector x1, x2, so a bivariate normal, and then also with a vector of t. Here, just use the definition: t transpose multiplied by a column vector of mu plus 1/2 t transpose sigma t. Here, just write x as a column vector 2 by 1 is x1, x2, follow a bivariate normal mu 2 by 1, sigma 2 by 2. Okay. So that's a known formulation that coming from the multivariate normal. We can also set another equation. Maybe I'm just using the right hand, this part. This is also equal to the expectation e raised to the power of, here we're going to use the scalar version, t1 y1 x1 plus t2 x2. So x is ranging from 1 to 2. This is referring to the coordinate, not how many observations that you have. Okay, yeah. Next, maybe you can also write down one more formulation just to make it coming from here. This is just referring to t1 mu1 plus t2 mu2, and then yeah, this is just expanding this by in terms of a scalar. 1/2 t1 square sigma 1 square plus 1/2 t2 square sigma 2 square plus 2 copy of and then multiply by 1/2 and then the covariance. So t1 t2 sigma 1 2 or 2 1. So this is sigma. Okay, so this is just elaborating from the vector matrix multiplication into a scalar form. And then now we're just going to bridge between these two. Okay, and then back to our original question. y1 raised to the power of 3 with the definition of y1 equal to e raised to the power of x1. This is by definition here. And raised to the power of 3. So here we just started with the quantity of interest that we want to find, and then let's see if we can bridge from the known information. Equal to e with expectation of a e raised to the power of 3x1. Okay, so after you recognize y1 raised to the power of 3 is essentially this. Now we can bridge between this, and let me just point it out, and then I will erase this. We're going to bridge with that. And you can find, you can evaluate this quantity by setting T1 equal to 3 and T2 equal to 0. So that will be our strategy here. Any question up to this point? Okay, then the rest is just plug in. So this, yes, and then we can, using this form here, if you want to be, yeah, so let me just erase all these things. Okay. So you can, so now we're just going to borrow this copy here and plug in the things that we recognize with T1, T2. So T1 is 3 multiplied by mu1 as a scalar plus 0 multiplied by mu2 plus 1/2 9 sigma 1 square, 0 and 0. Okay, so that will be our final solution for y1 cube. Any question? So this is just plug in the things that we read out from the yeah. Any question? Yeah. Sorry, what? You mean this part here? Yeah. Just t equal to 0. Yeah. Any other question or comments? Okay. Then we are interested in the covariance as well. y1 and y2 cube. I'm going to use the definition for the covariance. y1 cube, y2 cube minus expectation of y1 multiplied by the expectation of y2. I think this can be found from the previous, right? Yes, and then for y2, this is just mu2 and sigma 2. So the question is how to evaluate these things. Let's plug in the expectation of 3x1 multiplied by the expectation of e raised to the power of 3y1 as 3x1 and 3x2. Yes. And then the product of the exponential is the exponential of sum. So we have expectation e 3x1 plus 3x2. And then, yeah, from here, we can just bridge again with this. So let me just draw a line here. Evaluate at T1 equal to 3 and T2 equal to 3. So plug in the T1 and T3, T1, T2 equal to 3 in this formulation. You will get the first part and then minus the expectation of the individual, and then you will get your final solution. Any question or comments? Okay. Next, let's talk about exercise 5. So join, okay, x1, x2, x3, IID from univariate normal 0, 1. And we have y1 equal to x1 plus x2 plus x3. y2 is x1 minus x2. y3 is y1 minus x3. Individual xi follow I from 1 to 3 normal scale univariate normal. We are interested in the joint of y1, maybe I'll use f for the PDF. We are interested in the joint of y1, y2, and y3. Okay, so first use the Jacobian, and the second one use the momentary function. Okay, so we can write f of x1, x2, and x3 as the product because of the independent of x of y1, x1, x2, and x3. Each of them having a 2 pi sigma square root. Oh, sigma square is 1. Okay, then it just ease the formulation. 1 over square root of 2 pi e of xi square minus 0 over 1. So is there 1/2? Yes. 1/2 xi for I in 1, 2, 3. Okay, so you can just plug in as and then make sure you have 3 copies of that. For Jacobian, we just need to find the transformation between x and y. So here we can write y2 plus y3 as 2 copy of x1 minus x2 minus x3, and then y1 plus y2 plus y3. This is just 3 copy of x1, and x2, x3 cancel out. Okay, so here we get x1, it's 1 over 3, y1, y2, y3. And then if you plug in the x1 into both either y1 and y2 and y3, you will get x2 is equal to 1 over 3 y1 minus 2 over 3 y2 plus 1 over 3 y3. Similar for x3, 1 over 3 y1 plus 1 over 3 y2 minus 2 over 3 y3. Okay, so maybe you can also double check just in case if I have a typo here. So here we have a relationship from each of the y as a function of all the x's. Here we also have a function for each of the x in terms of as a function of all the y's. And the reason we need this is that we need to calculate the Jacobian. I'm erasing things. It's not that it's not correct. It's just I need some space there. So don't take it. Yeah, it's not wrong. It's just I'm just making more space. Yeah. Okay. Once we have that, we just calculate the Jacobian, and then you can have dy1, dx1, all the way to dy3, dyx3. Just fill in the formula. So I start from dy to dx, then this is equal to 3. So you can double check. And then here, let me just write down the final solution. So here we are interested in y1, y2, and y3 for the joint. Here you need to use the product of the marginal of the x, but make sure you bring the copy or substitute the x with y. And you will have something like 2 pi 3/2 e raised to the power of 1/2, and then a very long form here. So just plug in the x1 square, x2 square here. Yep, and it will be a very long form because you need to take the square of x1, take the square of x2, and take the x square of x3. Yeah, and then after that, don't forget the Jacobian, 1/3, the inverse. Yeah, that will be your solution. We also have a part 2 for writing of using multivariate normal distribution property. So we can express that as a matrix and vector multiplication. So here we're going to design a 3x3 matrix multiplied by x1, x2, and x3. So based on that, we have 1, -1, and 0. 1, 0, -1. So y is equal to a multiplied by x, where x is following a normal 3-dimensional vector of mu and sigma. And the mu is essentially just 0, and then the sigma matrix is identity, 3x3 identity matrix. Yeah. And this matrix here is designed based on our formulation or our definition for the y's here. So you can also write 0 multiplied by x3 and then plus 0 multiplied by x2, so that you can see that equation here is essentially a matrix vector multiplication. So this is the 0 for x2 and 0 for x3. Yeah. So you can write a bunch of equations into a vector matrix multiplication. Once we have that, y is also going to follow a 3-dimensional normal with a multiplied by mu and a sigma a transpose. The reason that it's normal distribution is because y is a linear transformation of a random variable x. X is normal, a linear transformation of a random variable that is following normal distribution is also a normal, so that's why it's normal. And then e of y, it's e of ax, a multiplied by ex, a multiplied by mu is actually 0 because mu is a 0 vector. Variance of y is a variance of x, a transpose, and this is identity, so you only have a transpose. So this should also be a 3x3, and this is a 3x3. This is a 3x1. So you just need to calculate your a transpose here. Okay. Once you have that, you just need to plug into the formulation of a multivariate normal. So f of y Here, this y is referring to a 3 by 1 vector. 1 over 2 pi raised to the power of d over 2. Here, d is equal to 3, the dimension. Exponential of 1/2. Yeah, beside that, there's also one copy of the, let me just put it here. You have the determinant of the sigma star, which in our case is the A transpose here. So this sigma matrix is not the same as the sigma matrix for X. This is the sigma matrix for Y. So if you want, you can denote as a sigma star. The determinant of that altogether raised to the power of negative 1/2. This is just, everything here just the definition of a multivariate normal. So it's not something we come out, it just we just plug in the terms for here. Exponential of y minus mu, you can refer this as a mu star transpose sigma star inverse y minus mu star negative 1/2 of that. Yeah. And then plug in mu star is the zeros. Sigma star is the A transpose. And then after you plug in the numbers, you will find out that your solution for this multivariate normal is the same as the one that you get from here, from the Jacobian version. They should be the same. Okay, so for this question, it's just lots of plug-in and then using formula. So there's nothing very fancy going on. Just identify the terms and then plug in the numbers. Yeah. Any question or comments? Yeah, this one is just a very laborious and maybe tedious, but just plug in the forms. Yeah. Any question, comments? Okay, if not, then let's talk about question 7. Okay, so here y is a n-dimensional vector with a column of mu and sigma. So everything is n by 1, n by n. Okay, we define y as also q1 and q2. So basically two subvectors, a partition of y, and also mu1, mu2. So you can refer them as a n1 by 1 subvector and an n2 by 1 subvector, and such that n1 plus n2 equal to n. You can also partition that as y sigma 1 2 2 1 sigma 2 2, and then with the corresponding dimension. Okay, we also have a matrix A such that sigma 2 2 is sigma 1 2 or sigma 2 1. Let U be Q1 minus A multiplied by Q2. The A is defined based on this definition, and V is just, let me put 0 here plus Q2. Okay, a 0 vector. Find the joint of U and V. Okay, so same idea. going to write U and V. Let's see. Okay, maybe not comments on the dimension because the dimension here may vary, but they are just make sure that they are aligned. Okay, we're going to write U and V in terms of Q1 and Q2. So I'm not going to comment on the dimension here anymore because they're just different subvector, can be varied. Let's write this as I and negative A for a also a like a matrix but in a partition. Here we have 0 and identity. Yeah, so you can multiply Q1 and Q2 by identity and minus A, you will get the U here. And also Q1 multiplied by 0 plus Q2 multiplied by identity, you will get this V here. So maybe let's just call this a matrix of a B. And then you will have like a, I don't want to abuse the notation, but let's see. Here I just want to refer to the previous question. You basically have a form of a vector. It's a matrix multiplied by another vector. So a vector is a matrix multiplied by another vector. And then, yes, Q1 and Q2. Okay, this can be called as Y. And we have not used the notation X, so maybe we can use X is equal to BY, where Y follow this mu and the covariance matrix. Okay, so then we are interested in the U and V. So U and V, this new column vector following a normal. I'm not going to comment on the dimension here, but this is just B, the matrix B that we define here, multiplied by mu, the mu coming from Y. So this is the mean vector of the Y's because it's just a linear transformation of Y. And then you will have a B multiplied by sigma B transpose. Yeah, and then for the rest, I think you can just maybe just complete this question. Yeah. So the expectation of B multiplied by Y is just B multiplied by expectation of Y is just B multiplied by mu. And here we just have I, negative A, 0 identity multiplied by mu1 and mu2 from the partition. And this should also be a 2x2 block vector. So mu1 multiplied by identity minus a matrix multiplied by mu2, a subvector of the mean, also mu2. Okay. So I think this should still be n by 1 because this is just a partition of mu1 and mu2, so it should still be n by 1. Yeah. But I'm just not going to comment on the dimension. So yeah, this is just the mean here. This is just B multiplied by mu. Okay. Now let's comment on the variance of B multiplied by Y. It's B multiplied by variance of Y. Yes, yeah. Let's we call that B. Okay. Yeah. And here we just need to plug in identity negative A, 0 identity. That's the matrix B. Variance of y is the sigma 1 1, sigma 1 2, sigma 2 1, and sigma 2 2. That's that. And then B transpose. Okay, we have identity on the diagonal, and then the negative A is here, and then the 0 is here. This is referring to B transpose. So we change the we take the transpose of the B matrix. Okay, then the rest, maybe I'll just finish it. I'll just finish the discussion by finishing this question. So we have sigma 1 1 multiplied by identity minus A multiplied by sigma 2 1. That's the first element in the column. So here I'm referring to the block 2 by 2, 2 by 2, and 2 by 2. So you should also have a 2 by 2 for the first two multiplication. Okay, sigma 1 identity minus 1 and that, and then 0 plus sigma 2 1, and then sigma 1 2 minus A multiplied by sigma 2 2, and 0 plus sigma 2 2. Okay, so this should also be a 2 by 2 block matrix multiplied by the remaining B transpose here. Okay, so in the end you should also have a 2 by 2 matrix, a 2 by 2 block matrix. Okay, so sigma 1 1 minus A sigma 2 1 minus A sigma 2 1. Is that correct? No, I don't think. Yes, I don't think that's correct. So identity multiplied by that, and then negative A multiplied by sigma 1 2 minus A sigma 2 2, right? Is that correct? So row column multiplied by row, so I multiplied by that, negative A multiplied by that, so yeah, comma. Maybe we'll do it in the end. Yeah. Yeah. But yeah, you can do it now. But since I started the long way, maybe I'll do it in the end. Yeah. Maybe that would be easier. Your way will be easier. Yeah. And then sigma 2 1 minus a sigma 2 2. That's the first one. So the first column multiplied by the 2 row, and then 0 plus identity multiplied by that, minus a sigma 2 2, and this is sigma 2 2. Okay. Yes, and then maybe we can make the substitution to make it yes. So just let me double check if I yes, and then if you maybe you can just make the substitution here. You will have the off diagonal elements are zeros because the A is defined in a way that 2 1 and sigma 1 2 are equal to A sigma 2 2. So you have all the off diagonal elements cancel out. You have this as sigma 2 2 remain, and you can double check after you do the simplification. Yeah. Okay, and what was the question again? Find the joint. Okay, so we have so y u and v follow a normal with the mean here. Let me just call this a mu star, and let me call this as a sigma star. So make sure you just plug in the mu star and sigma star here. Okay, so that's that. For part B, show that Q1 conditional on Q2 following that. I think for the conditional one, you just need to plug in the corresponding component to the formula and then make sure you make the substitution for the A sigma 22 and sigma 12. Then you will have the final answer for the mean and the variance. And then I will leave it to you to double check if you can get the same mu and the sigma by plugging the formula and then get the same mean and the variance there, just using the conditional formula. I'm not sure what does it look like, but maybe it's a very long one from your handout. Just plug in. So this part is just plug in the component and then simplify. Okay, I think I'll just stop here. And okay. Let me pause the